Welcome to this webinar on seized drugs analysis. My name is Khalid Khan from the Waters Forensics team, and I will be moderating this session. Firstly, I would like to thank you for taking the time to join this webinar, which I hope you will find both interesting and useful. In this webinar, we will have two Waters scientists from the Forensic Applications team presenting on two innovative mass spectrometry solutions that we believe can improve seized drugs analysis and therefore potentially change the current paradigm of seized drugs analysis. I'd like to take a few moments to explain how the ON24 platform works. If you have logged on properly, this is the view you should have on your computer screen at that moment. In the center of the screen, you will see the presentation, and in the top right-hand corner is the presenter. After the presentation, we will have a question and answer session with our two speakers. If you have any questions, please submit them by typing the question in the top left-hand corner of the screen. We will attempt to answer as many questions as possible live. Those that we don't have time to get to, we will answer at a later date by email. But a couple of other features I would like to point out are the resource center, which you can see on the bottom left of the console. Here you can access information on the products and applications covered in this webinar, such as brochures, application notes, and posters. We would also like you to complete a very short survey, which you can see on the bottom right of the screen. For colleagues who may be interested but couldn't make it today, this webinar will be available on demand for at least 12 months. Now I would like to introduce our two speakers today. Both our speakers are application scientists specialized in forensic applications in drug identification and toxicology. Nayan Mistry joined Waters in 2009 and is now a senior application scientist in the forensics team. Nayan is part of the global team dedicated to the development of applications in underscore solutions for forensic drug analysis and toxicology. Nayan's key focus is screening, and he has expertise with both nominal mass and accurate mass-based mass spectrometry screening solutions. Nayan plays a key role in the development of these solutions and in the expansion of associated libraries. One of Nayan's favorite activities is customer interaction and customer support. Nayan is involved in numerous global customer support and training activities and has presented his work at conferences worldwide. Emily Lee is a recent recruit to the forensic team at Waters and is now also part of the forensic global team dedicated to developing analytical solutions for forensics and toxicology. Emily has wide experience on a number of Waters mass spectrometry techniques for the analysis of forensic and toxicology relevant analytes. Prior to working at Waters, Emily has experience working in a forensic toxicology laboratory with high sample turnover and fast turnaround times. Emily was involved in many aspects of day-to-day laboratory operations, including sample extraction, analysis, method development, and validation. Our first speaker today is Emily, and I would now like to hand you over to Emily.
Hello, and welcome to today's presentation. As you can see from the title slide, this presentation focuses on the topic of seized drug analysis. Today, my colleague Nayan and I would like to introduce two different mass spectrometry systems and demonstrate how we have been using these for seized drug analysis and how they might fit into a workflow to improve laboratory efficiency.
Here is an outline of the presentation. I will start with a brief introduction to the challenges faced currently, before introducing you to the RADIAN-ASAP system, which we are using for fast screening. I will then pass over to Nayan, who will present on the ACQUITY RDa Detector and how he has been using this for confirmatory analysis.
The analysis of seized drugs plays a vital part in the effectiveness of national and international programs. These aim to control the use, trafficking, and distribution of illegal drug substances. Drugs can be seized from many places by police forces and border control. A few examples of these are shown on this slide.
Due to the extensive number of samples seized and submitted for analysis, a huge burden is being placed on drug control laboratories currently. Industry guidelines stipulate that 2 independent analytical techniques should be used to analyze a drug sample that has been seized. Traditional workflows usually comprise of a presumptive screen such as TLC or colorimetric tests, followed by a more selective method such as GCMS or LCMS. TLC analysis can be time-consuming, and colorimetric tests are not available for all compounds, which can then result in a high rate of false positives. This can then lead to more samples requiring further analysis by GC or LC. This can then cause sample bottlenecks and backlogs within the laboratory. 2 new instruments from Waters which were developed in the last year or so are the RADIAN-ASAP, which is a direct analysis system, and the ACQUITY RDa Detector, which uses a chromatographic technique. These instruments could be used individually, slotting within a laboratory's current workflows with their existing techniques. However, myself and Nayan will be presenting an example workflow using both of these instruments in conjunction, with the RADIAN-ASAP being used as an initial screen, then confirmative analysis performed using the ACQUITY RDa. RADIAN-ASAP stands for Rapid Direct Analysis Atmospheric Pressure Solids Analysis Probe. The small footprint instrument combines the simplicity of ASAP with the specificity of mass spectrometry. As most of you will know, mass spectrometry is considered to be a powerful analytical tool, which offers high specificity. However, its adoption as a screening method within drug control laboratories has been limited. This can be due to the cost of ownership, the complexity of the equipment and therefore the expertise which is required to operate, and the long run times which are often associated with chromatographic separation. The RADIAN-ASAP is designed for rapid, easy and low cost per sample analysis, with minimal sample prep required and no chromatographic separation. Now we will look at the ASAP ionization process. The sample itself is introduced into the source on a disposable glass capillary. There is a stream of heated nitrogen which serves 2 purposes. Firstly, it provides a heat source to the glass capillary to volatilize the sample and create gaseous molecules. And secondly, it creates a nitrogen plasma in the region around the corona discharge pin, which is the basis of one of the predominant mechanisms of ionization. The nitrogen plasma indirectly creates ions from the volatilized molecules, which are then guided into the instrument and sorted on the basis of different mass-to-charge ratios before being detected and generating the mass spectrum. Now we'll move on to the mechanism of ionization. The main ionization mechanisms for ASAP are really identical to those seen with APCI. The first of the mechanisms is a charge transfer mechanism, which is initiated by the corona discharged ionization of the nitrogen in the ionization source. This generates radical cations of nitrogen, which can then undergo charge transfer with analyte molecules to generate the radical cations. This form of ionization is particularly useful for the analysis of nonpolar compounds, and typically is more prevalent in source conditions without the presence of protic solvents such as water or methanol. The second mechanism for ionization is by proton transfer. Now this requires the presence of water or other solvents such as methanol, which can act as a source of protons to form the ionized solvent clusters as shown. The ionization of the analyte then occurs by proton transfer, which is the main ionization pathway associated with APCI and LCMS. For this study, 66 unknown samples that had been confiscated at various music events and nighttime venues by police forces were analysed. For the powders, 10 mg of the sample was weighed out, and then 10 ml of 50-50 methanol water was added and sonicated. A similar method was used for the capsules, where the contents of the capsules were emptied and 10 mg was weighed out. For the pills, unconventionally compared to common practices, the whole pill was placed in 10 milliliters of 50-50 methanol water and sonicated. This was just done for ease and speed of preparation. Prior to analysis on the RADIAN-ASAP, these solutions were then further diluted by 1:20 in 100% methanol. For the analysis of the samples, a dipping technique was used, where for each sample, a new glass capillary was selected and cleaned using the Radian's inbuilt automated bakeout procedure. The cleaned capillary was then held just below the surface of the liquid, approximately 1 centimeter, for 5 seconds. After this, the capillary was then placed into the ASAP source. Here is a short video that summarizes the sample preparation and analysis when using the RADIAN-ASAP.
The RADIAN-ASAP is a compact mass spectrometer and has been specifically designed to be very easy to use. Samples are analysed directly, without chromatographic separation and with minimal preparation. Samples for testing can be crushed, or in the case of powdered or crystalline material, we can simply take a small amount of sample into the vial with a common solvent such as methanol. And then it's a simple action of pipetting or dipping the sample onto a clean glass capillary and loading that sample into the RADIAN-ASAP for direct analysis.
Data was acquired in positive ionization mode. Mass detection was performed using full scan over the range master charge 50 to 600. To further enhance the specificity, the data was acquired simultaneously over 4 differing cone voltages. This resulted in fragmentation and generation of both precursor and product ions for the compounds. Acquisition at the 4 cone voltages generates a spectral fingerprint, as you can see from the example on this slide, of ketamine certified reference material analysed on the RADIAN-ASAP. Identification of a compound is based on the identification of a precursor ion. The lowest cone voltage, in this analysis 15, typically contains the ionized precursor molecule. In this example, ASAP ionization has resulted in the generation of the protonated species at 238, which is ketamine. As you can also see, by ramping up the cone voltage, there are also product ions which are generated throughout. LiveID library matching software was used to process the results. This can be done in real time, where the data is processed live whilst the acquisition is running, or the files can be processed post-acquisition. The software is very simple and easy to use, therefore not requiring expertise to interpret the results. The library contains approximately 50 compounds. However, this can be expanded and added to by the user. The software calculates an average match factor of the data against the library using a reverse fit model, with a greater weighting being placed on the parent ion. A match factor of 850 was used as the reporting cutoff. The maximum match factor possible is 1000. On the next slide, there is a short video showing a sample being run using the real-time acquisition. First, you will see some background data being collected. Then once the sample has been inserted into the RADIAN-ASAP, you will see the response almost instantly. As the response begins to drop, you will see that the match factor score is being calculated simultaneously to then provide the results. An example of one of the seized samples analysed is shown here on this slide. This sample was analysed in triplicate, as you can see from the 3 datasets on the top left. The spectral data for the unknown sample, shown here in yellow, is matched against that for the reference spectra in the library, shown in blue. The individual match factors are calculated for the individual spectra at each cone voltage. Then, the weighted average is calculated to give the final score. In this example, that is 995 for ketamine. As the maximum match factor is 1000, this is a very good match score. On this slide, there is an example of a seized sample analysed which overloaded the system. As you can see in the top left, the data is highlighted in red and there is an error message regarding saturated scans. The LiveID software states that if this occurs, the match factor may not be as accurate. However, if this does occur, you can simply dilute the sample further using methanol and run again. Another thing to remember when using the RADIAN-ASAP is that the data in the top left are not chromatographic peaks, but a visual representation of the response. Therefore, they may not look as smooth as the peaks you get if you are used to using a chromatographic method. Here we have the results of the 66 seized samples analysed. Of these samples, 79% had a match factor score greater than 850 to 1 or more components within the library. There were 55 positive identifications made within the sample set. These involved only 7 substances. This may be due to where the samples were seized, as they were all seized from nighttime venues or music events. MDMA was the predominant compound detected, as it was seen in over half of the samples, and in most cases this was the only component detected. To assess the RADIAN-ASAP's capability of analysing mixtures, certified reference material mixtures with varying proportions of 2 different analytes were prepared and analysed. Here on this slide you can see a table detailing the match scores for a mixture of fentanyl and cocaine. Cocaine was detected at 5%, however at a match score which was below the reporting cutoff of 850. Therefore, the lowest positive result for cocaine above the cutoff was at 10%. Fentanyl was positively detected at 10% above the 850 cutoff, with no match detected at 5%. Most analyte mixtures showed similar results. However, they did show to be compound-specific. Here is an example of the LiveID results of the CRM mixtures discussed on the previous slide. On this slide is the 90% cocaine and 10% fentanyl mixture. So to recap, Waters are currently intending to increase the screening capacity by expanding the current library with more common drug substances. From this presentation, you will now see that the RADIAN-ASAP is a compact, robust, and easy-to-use system which enables rapid screening of seized drug samples. The LiveID library matching software offers easy-to-interpret results requiring minimal expertise, which can be typically obtained within 1 minute. This offers forensic laboratories the potential for a rapid, accurate triage of samples. I am now going to pass you over to my colleague Nayan to talk to you about the ACQUITY RDa detector, the next step in the workflow that we are presenting. Thank you for your time.
Thanks, Emily. Hello, everyone. My name is Nayan Mistry. I'm a Senior Application Scientist in the Toxicology Division at Waters Wilmslow, UK. In this 2-part presentation, Emily discussed the RADIAN-ASAP technique, and in this second half, I will focus on the ACQUITY RDa detector and how it can be used to complement the rapid screen. You have already seen a similar slide to this with Emily, where she discusses the various categories and techniques that are used for seized drug analysis and explains the minimum requirements for identification. The instrument I'm going to present here is the ACQUITY RDa Detector. It is a system which combines liquid chromatography with high-resolution mass spectrometry, and so it is a hyphenated technique. It satisfies the requirements and provides structural information that falls under category A and combines that with the physical property information that we can glean from category B. The ACQUITY RDa is considered an entry-level time-of-flight instrument that is easy to use yet offers a user accurate mass data to report with confidence. Traditional seized drug screening techniques such as TLC and infrared spectroscopy can identify common drugs of abuse but may not detect novel psychoactive substances. Any newly developed methods need to be easy to use, robust, fast and efficient. The method should have the flexibility to be updated, have the ability to elucidate and identify unknown peaks, and not have the added burden of performing time-consuming complex sample preparation. The ACQUITY RDa Detector is a small, high-resolution mass spectrometer which provides high specificity in identification. Compounds can be identified on the basis of their accurate mass to 4 decimal places, and the associated software has the ability to assist with structural elucidation of unknown peaks. The ACQUITY RDa is ideally suited to the fast-paced environment of a laboratory for seized drug analysis. It is an entry-level time-of-flight instrument that has been specifically designed to be simple and easy to use with the aid of SmartMS. The ACQUITY RDa Detector incorporates technology called SmartMS. The RDa has a one-button startup and pump-down sequence. The instrument setup is completely automated, and the software tunes all the important instrument parameters and calibrates the instrument. The front panel is an intuitive user interface to provide the current status of the RDa, and the software has a full suite of diagnostics for the UPLC I-class and the RDa detector to monitor the system's health. Here we have a schematic of the ACQUITY RDa detector. The analytes in the sample will be chromatographically separated by the mobile phases and column used on the ACQUITY UPLC I-class Plus before progressing to the electrospray ionization source. From here, the ionized samples enter the first stage of the stepwave ion guide, where we can ramp up the voltage to induce fragmentation that is used in the identification of the analytes. The second stage of the stepwave ion guide is the segmented quad. This helps focus the beam into the pusher region of the TOF. The short pass of the ion guide 2 and the transfer lens ensure greater ion transmission efficiency. The TOF is in a V configuration that is half a meter in length and houses a dual stage reflectron. As you have seen already in Emily's presentation, a number of seized samples which were confiscated at music events were obtained from the local police constabulary. The methanol water dissolved material were further diluted 1 in 20,000 prior to analysis on the ACQUITY RDa detector. The following slides summarizes the ACQUITY RDa analysis method. Data is acquired in positive ionization mode and separation occurs on a 10 cm ACQUITY HSS T3 column over a 9.5 minute gradient elution whilst using mobile phases A and B. Data is acquired using full scan accurate mass with fragmentation mode. Not only do we get accurate mass to 4 decimal places on this instrument, but we can also perform fragmentation which provides additional information that can be invaluable during the identification process. Fragmentation is induced by an increase in cone voltage energy from 70 to 130 electron volts and occurs within the source region of the instrument. Let's take a look at why fragmentation is so valuable. Let's consider the molecule MDMA. For comparative purposes, on a nominal mass instrument, we can see that the mass to charge in positive electrospray ionization is 194. However, when we use an accurate mass instrument, we see a significant improvement in specificity as we are now measuring to 4 decimal places. If we take this a step further, you can see the additional information we obtain by enabling fragmentation. Not only do we have the accurate mass of the precursor, but we can also measure fragment ions to 4 decimal places too. These fragments can be used to provide an extra parameter during identification, but can also, in some instances, be used to differentiate between isomers. This slide shows an example where the use of fragment ions can provide differentiation between some isomers. As you can see here, the precursor accurate mass for both isomers are identical. With the presence of additional fragment ion information, it has allowed us to differentiate between the two molecules. The acquired LC-TOF data was processed against a target list comprising of more than 100 common drugs of abuse substances. The software used for data acquisition and processing was Waters Connect. This slide summarizes the main classes of drugs that were included in the list. Each entry has an associated retention time and fragment ion information that were obtained from data acquired using the high-resolution mass spectrometer. One point to note is that the library is flexible and can be expanded and customized by the user. A positive identification was based on retention time, the presence of a precursor ion, and the detection of at least one diagnostic fragment. This slide illustrates a typical example of a library entry. The entry shown here is of the compound alfentanil. Every entry in the library has a precursor mass, fragment ion information, an associated retention time, and a chemical structure, or mol file. A mol file is a very useful addition to the library entry, as it provides elemental composition and arrangement information. The software uses the mol file to generate theoretical fragment ions based on the fragmentation data obtained during acquisition. Updating the library to include new entries such as novel psychoactive substances is very easy. Simply download a mol file from an online database such as ChemSpider, create an entry in your library, add the mol file and start to screen for them, even if you don't have the material.
Data is processed using quite lenient parameters. These include a retention time tolerance of plus or minus 0.35 minutes, a minimum precursor and fragment ion intensity of 250 and 5 counts, and a mass error of 20 ppm and 2 millidaltons respectively. Use of broad criteria ensures a metaphorical wide net is cast to capture any significant compound identifications. These identifications are further processed with the aid of workflows. A workflow contains a set of customized filters and defined parameters which display data harvested from the initial processing step and is presented in a tiered arrangement from the most confident result to the results that require a little more investigation. What we have here is an example of a workflow filter for the positive identification step. Data displayed using this filter have satisfied the minimum peak area response with a good mass accuracy, and at least one expected fragment ion has been detected. This filter is designed to provide the user with good confidence in identification. As you progress down the workflow list, the filter becomes more lenient, which invariably lead to a higher number of identifications.
This is a review tab in Waters Connect. What you will see here is just one example of a sample which was found to contain cocaine, and we can see the wealth of information that the ACQUITY RDa provides. As previously described, a positive identification was based on the presence of the precursor ion with good mass accuracy, all expected fragment ions detected, and a retention time within plus or minus 0.35 minutes of the reference retention time. The spectral data on the right displays the precursor ion in the top spectra and the corresponding fragment ions in the lower spectra. This is together with the pictorial representations showing the intact precursor molecule and the fragment portion of the molecule that the measured mass relates to.
As you are aware, the Waters Toxicology Library is a comprehensive repository containing a suite of information for toxicologically relevant compounds. However, not every compound is contained within this library, and there may be instances where a peak is detected but not identified or matched, as that substance may not be in the database. In those instances, the Elucidation Toolkit is a very powerful feature. An unidentified or unmatched peak is deemed a candidate peak. The candidate list is arranged based on the largest peak area response at the top. In the example we have here, it's a peak at 3.38 minutes with a response area of over 900,000 counts. From here, you simply right-click on the candidate of interest and select Elucidate. Selecting Elucidate will send all the information pertaining to the candidate peak to the Investigate tab and start the elucidation process. The first step is to determine the elemental composition. Once a plausible elemental composition is proposed, it is then sent out to search against a user-defined online database in ChemSpider to retrieve potential compounds matching the composition. The retrieval process also returns with their respective mol files. The software postulates theoretical fragment ions using the mol files, which are then matched to the fragment ions in the high energy spectrum. Once satisfied, the user can assign the peak with the proposed compound identification. In this case, it was ChloroFentanyl.
Presented here is a results summary for the 66 Cs samples which were analysed using the ACQUITY RDa detector. 79% of the samples were matched to one or more components in the library. There were 61 positive detections made in the dataset, and a summation of these substances are shown in the graph here. MDMA was the most prevalent substance detected and was identified in over half of the samples tested. You may recognize that this dataset is very comparable to that shown earlier by Emily for the rapid screening analysis. On the next slide, we compare the RADIAN-ASAP results with the ACQUITY RDa findings. Let's take a look at them now. This study demonstrated the analytical workflow with the RADIAN-ASAP and the ACQUITY RDa detector, showing good qualitative agreement with concordance for 90% of the drug detections. In addition to the analysis performed using the two systems discussed, the 66 C samples were also analysed by an independent QTOF broad screen as an established reference technique. A comparison of the data between the RADIAN-ASAP and the ACQUITY RDa detector highlighted some differences. In 3 instances, discordant samples were due to the variation in library content. Identifications were not possible as the substances were initially missing from either the RADIAN-ASAP library or the ACQUITY RDa list. 4 samples tested positive on the ACQUITY RDa but were initially classed as negative by the RADIAN-ASAP. Following further investigation, the substances were shown to be present in the RADIAN-ASAP data. However, they gave matches which were below the minimum match factor threshold of 850 or 85% that was applied during the analysis. A further 2 samples demonstrated discordant results. MDMA and paracetamol tested positive on the RADIAN-ASAP but were negative on the ACQUITY RDa detector. Further interrogation of the RDa data indicated the presence of a small chromatographic peak. The data was submitted for structural elucidation using the software, and it did propose MDMA as a plausible identification. The second discordant sample was also subjected to the same degree of investigation and was proposed as paracetamol. This preliminary proposal was also supported by the analysis on the QTOF, and the samples were subsequently reanalyzed on the ACQUITY RDa following a lower dilution factor. And finally, both techniques were negative for the same 11 samples. The RADIAN-ASAP and the ACQUITY RDa detector are two flexible techniques that have demonstrated their potential of being used for seized drug analysis. Here we have illustrated one way in which these instruments can be utilized in the form of a complete workflow. The RADIAN-ASAP for a preliminary screen and the ACQUITY RDa for a subsequent confirmation analysis. The RADIAN-ASAP has been shown to be a rapid screening technique that is effortless to set up and use. Sample preparation is a simple dilution, and results are obtained within minutes with the use of the LiveID software and expandable library. The ACQUITY RDa has been shown to be an easy setup and use accurate mass system. There is no need for complex sample preparation, simply dilute and inject. The ACQUITY RDa is considered an entry-level time-of-flight instrument that offers accurate mass data and provides a novice user with confidence in reporting results. A library that is flexible, expandable, and customizable is also available for the ACQUITY RDa. Unidentified peaks can be identified using the Elucidation feature in combination with the external libraries such as ChemSpider. Overall, both techniques have demonstrated their ease of use, affordable price, and small footprint, making it an ideal fit for seized drug laboratories. Further reading material in the form of an application note is available for both RADIAN-ASAP and the ACQUITY RDa detector. A webinar is also available upon request. Emily and I would like to take this opportunity to thank Dr. Michelle Wood for her continued support throughout this project.
Thank you all very much for your attention throughout this presentation. I will now hand you back to Khalid. Thanks, Khalid.
Thank you, Nayan, for that presentation on the ACQUITY RDa, and thank you, Emily, for the presentation earlier on the RADIAN-ASAP. Emily and Nayan are now both available to answer your questions. We have already received a number of questions, which I will read out shortly. If you have any questions, you still have time to send them in. Just type them in the top left-hand part of the screen and send them in, and we'll try to answer as many as possible in the time available. Thank you. Thank you today, Nayan. Thank you for joining this webinar. We still have time for you to put the questions in, put them into the box in the console, and we'll try to get as many questions as possible in the remaining 15 minutes or so. We have questions already in. I'll ask the first one is now. The first one is regarding the RADIAN-ASAP. For Emily, can you explain the bake-up procedure for the capillaries to bring something on?
Hi, yes, so the bake-up procedure is an automated process where it increases the temperature, that's for a fixed time period of 1 minute. This removes any contaminants off the capillary, such as the components from manufacture process.
Thank you, Emily. Sorry, I think I was on my phone line wasn't working then. Can you hear me now? Just if you type in the team chat.
Yes.
Fantastic. So in case you missed me earlier, so I'd like to thank the two speakers, Nayan and Emily, and I'd like to thank you for all attending. There's still time for you to enter your questions. You can just add them into the type them into the console, and we'll try and get to as many as possible in the remaining 15 minutes or so. Another question that's come through on the RADIAN-ASAP for Emily. In the presentation, you talked about using LiveID in live mode. Can you also use it in post-processing? And are there any advantages or disadvantages of either approach?
You can use both. It's really just a matter of personal preference, depending which people feel they prefer. I usually use post-processing because I normally run all my samples and then go back and look at all the results as one big lump rather than doing it one by one, but it really just depends on what you prefer.
Okay, thank you for that, Emily. Another question on the RADIAN. Can you access the raw mass spec data?
Yes, you can open that up through mass links.
Okay. Another couple of questions on the RADIAN. How does the system cope with a high concentration sample that suffer from contamination?
So I've run samples which were high concentration, and as it showed in the presentation, you get the error message saying that you've got saturated scans. But I've never seen any contamination of the instrument or carryover into the samples that are run after samples that do become saturated. So I don't think that I've never seen contamination of the instrument.
Okay. We have a question here. Can the rate, so in the presentation you showed sample introduction by dipping the capillary into a solvent. Can you also analyze direct analysis of solid powder samples without dissolving methanol water first?
I haven't tested that, and I don't think any of my colleagues have, so it could be something that we could look into, but as of yet I don't really have an answer to whether it is possible or not.
Okay. We can follow up with that one later by email. This is a question for both the RADIAN and the ACQUITY RDa. How easy is it to add a new compound to either library? Maybe you can ask Nayan first, as you've not answered one yet.
Hi everyone. It's very easy. I mean, I did explain how to add a new entry into the library. It's simple. You just download a mol file or structure from, say, an online database like ChemSpider, and create an entry within Unify, and just import in the structure, and then you can literally just screen using that information. Because once you've imported in the structure itself, it brings in all the relevant information like the formula, the mass, and so on and so forth. It doesn't bring in any fragment ion information that you have to deduce yourself through the experiment of doing accurate mass with fragmentation, but that's easily done and modified at a later date. Emily?
So I've not actually added anything to the library of RADIAN, but when I spoke to my colleagues that have, they have said that it's very simple. It's through a third-party software called MSP Librarian, and we do have documents and support available if people did want that.
Okay. Question on the RDa. How often do you have to calibrate the RDa in terms of mass calibration? For you, Nayan?
Yeah, so with regards to calibration, the system itself is pretty intuitive. It's got SmartMS. As I mentioned already, the system upon startup does go through the process of checking calibration and resolution. If it's happy with that, it'll obviously allow you to go forward and perform the analysis. If it's not, then it will basically flag up to say it needs to be one or both need to be redone. So, and prior to every injection, there's a calibration and resolution check as well. So there's always checking going on with regards to the two in the background. So the results you're getting are obviously good from the calibration and resolution checks.
Okay, thank you for that. There's a question on the RADIAN. Can you perform quantitative analysis on the RADIAN?
I've only used it in a qualitative mode. I wouldn't consider it to be a quantitative instrument. However, I think it might be possible to do semi-quantitative work if there was an internal standard added to the sample. As of yet, we haven't tried that.
I think I've recently seen some publications where people have added an internal standard at known concentration, so maybe I can forward those.
Yes.
Yeah. In the video, we saw you just dip the capillary into a sample before inserting it into the radian. Can you also pipette a known amount on the capillary, and are there any advantages in using pipette?
Yes, you can do that. As far as advantages and disadvantages, we haven't seen any difference in the results. So once again, it is just a preference of what you personally decide to do.
Okay, thank you. There's a question for on the RDA for Nayan. Do you use lot mass? How does the system ensure good mass accuracy?
Yes, so lot mass is used in the form of leucine Keflin, and there are 2 points taken per sample. So there's one sampling taken of the lot mass at the beginning of the sample and one taken at the end. That's the default. You can actually modify that and have it sample as often as the user wants, really. So yes, the short answer is yes, it is used. We do use lot mass.
Okay, thank you. You mentioned again on the RDA talk, you compared the samples with a broad screen QTOF. I assume you mean something like the Xevo QTOF. How does the RDA compare to high performance instruments such as the Xevo QTOF range? Right.
Yeah. So so the RDA is, if we go back a step, the RDA is a very, they're both high resolution mass specs, but the RDA is of a lower sensitivity. So the Xevo G2XS QTOF does have a better performance than the RDA, typically between 5 to 8 times better, and is typically used for more demanding applications, whereas the RDA is kind of, we're kind of aiming for the SWGDRUG analysis market, really. It's an easy setup instrument, obviously using the SmartMS. So with regard to the comparison between the RDA and the Xevo G2XS QTOF, the QTOF is more sensitive than the RDA. But for works with SWGDRUG analysis, the RDA is a pretty good and sufficient instrument.
Okay, thank you for that. There's a question. I think this could refer to both talks. Maybe I could take this. Do you have to derivatize the samples as you do for GCMS? The answer to that is no. You don't have to derivatize any of the samples for either system. Just simple dissolving in methanol is sufficient sample prep when you're analyzing SWGDRUGs.
Yes. So with regard to the RADIAN, it would be a simple dilute and shoot, or dilute and dip, sorry. Whereas the RADIAN, you would obviously need to dilute the sample and then dilute the methanol out to avoid, sorry, the RDA, not the RADIAN, the RDA, they all sound the same. Yeah, the RDA, you would need to dilute out the methanol to avoid the tailing on peaks and so on and so forth. So there would be slightly more preparation for the RDA than the RADIAN, but in all essence, you can use the same sample from the RADIAN to the RDA.
I think we've pretty much covered all our questions. So once again, I'd like to thank our two speakers, Nayan and Emily, for excellent talks. I would thank the audience for attending. And if your question hasn't been answered, it's because we weren't made entirely clear, so we'll follow up with emails on that. And again, if your colleagues couldn't attend this webinar, the webinar will be available on demand for 12 months. Please forward it to colleagues who could be interested. But once again, thank you and goodbye.